we agree that we have some serious commitments to preserving the invariance for any model that we actually construct. In this case, the initial model of our bridge controller. And how can we really achieve this formally? So the answer is we want to really adopt a formal proof system, so-called natural deduction, in which case we're going to use the so-called sequence to really do a series of proof steps, and hopefully we can make sure every proof obligation that we formulate as a sequence can be proved as a tautology or as a theorem. That's something we'd like to do throughout the course. Right, let's now just talk about the basics first. We want to first understand what a sequence is. You may have already seen the syntax for sequence maybe in your earlier math course, but that's okay. I'm going to teach you from scratch just to make sure everybody will be standing on the same ground to begin with. Right, let's talk about both the syntax, how you write it, and also the semantics for its meaning, both informal meaning for you to easier for you to remember, and also the formal meaning for you to know precisely what it is about. Let's see. And we're gonna use this syntax over here. I'm gonna talk about the syntax in just a moment, but we're gonna formulate each. Remember PO and also VC, right? What are they? Proof obligation or verification condition rule, right? As a horizontal or vertical sequence. Well, basically every proof obligation or verification condition rule, they're gonna focus on certain aspects of the commitments that we make to our system. And the one we're talking about right now is so-called invariant preservation. So just don't forget, right? Later on, we're gonna see other kind of proof obligation or verification condition. For example, refinements or maybe deadlock freedom. That's something we'll see in the later weeks. But for this week, we only concentrate on invariant preservation kind of proof obligation. Okay, and let's talk about the syntax very quickly. Right? If you look at syntactically, how you write is you're going to write a symbol over here is so-called turnstile over here. You can see this guy over here, right? That's how you write it. It's called turnstile. For those of you who might be wondering about why this will be the term for this symbol over here, you guys might be too young to really appreciate this. The reason that it's called turnstile is because you can definitely just Google for example, you can Google for subway and then turnstile. So this is actually the old system where people who actually want to pass the gate, they got to pay first before they take the subway, and then before they pass the gate to reach the platform. So there's something called the turnstile as the blocking gates to make sure everybody pays before they actually get to the platform for the subway. I believe in Toronto, in many subway stations, they're still actually adopting this system over here. But I think in many other more advanced subway systems, they don't use the turnstile anymore. But you can definitely check it out on the Google, right? I'm gonna let you do that historical research on yourself, right? But anyway, so the symbol over here is called turnstile. I'm gonna talk about the meaning a little bit later. Let's now focus on how you write it. You can either write it horizontally, in which case there will be something to the left and there will be something to the right. And you can also write it vertically. So it will still be the same turnstile that you have to write over here, but you got something on the top or something on the bottom, right? Just to notice that if you write it this way or if you write it this way, the left and the top, they are referring to the same thing. And also the right and the bottom, they also refer to the same thing. That's why I'm using the same symbol. But now we need to know exactly what they really mean, right? Let me go over the bullet points and then I'll come back to the slide to do some annotation. And so far, we only learned about this symbol is called turnstile, right? Let's now go back. Let's now do some anatomy of the syntax over here. So the symbol is called the turnstile, and H over here on the left or on the top is so-called the hypothesis or assumptions. But here you want to make sure you remember this. Whenever we talk about this part over here, it may be simply a set of predicates. And whenever I say a set, that means the set might be empty, meaning that the H over here may be simply absent, in which case we simply got an empty set of hypotheses, right? It's called hypothesis or assumptions, meaning that they can simply assume to be true, right? So let's annotate right away, okay? So we talk about this part over here, the H over here, and also the H over here in both forms. So these two over here a so-called hypothesis. Or assumptions. And what's really important for you to note is they are a set of predicates. A set of predicates. By the way, they're simply just a set of predicate that we the ones that we review in the first 2 weeks. It cannot be nested turnstile. You don't have that. You cannot say that you simply got H over here. It's another nested turnstile. No, it's not possible, right? Luckily, right? It's not the case. And the set over here might be empty. Might be empty, in which case I will explain exactly what that means. It's actually one of the questions I will ask you once we explain the semantics for the turnstile, for the sequent. All right. So that's about hypothesis, and they're assumed to be true. All right. So this part here is assumed to be true. So they are simply assumed as true. More like an axiom, right? Something that you assume to be true, and you want to prove something else using it. And what about another component, which will be the right and also the bottom, the G over here? What does it really mean? So G is a set of predicates forming the goal and conclusion. Again, it could be a set, all right? And they're claimed to be provable from H, meaning that by assuming the hypothesis, it should be provable that H is actually true. Oh, sorry, it should be provable that the G is actually true. Let's now do some annotation here, right? So here we got the G over here on the right, and also the G over here at the bottom. So they are referring to the same thing, which is called the goal. Okay, so they are called the goal of the sequence. Also a set of predicates. Indeed, if you say it's a set, you might be thinking about it might be empty as well, right? In theory, yes, but typically you don't really see this as empty. Should not be empty. Right? It's really important for you to know that. Okay? In practice, it should not be empty, because it's certainly something we would like to prove. Okay, and this part over here is something that should be provable, assuming the hypothesis H over here, which can be a set of predicates. In the case of H being empty, in that case you can assume nothing. In that case, it will be a more strong, like a stronger claim overall to really make. We'll see that. All right. All right. So that's about the syntax for the sequence. Let's now talk about informally what does it really mean when we actually got H turnstile G over here. What does it really mean? Informally, we say, one thing that's very important for me to emphasize. Whenever you write a turnstile like this or turnstile like that, vertically, right? Overall, when we actually say, let me just put it here. If I write, let's say, let me use also green over here. If I write, let's say, let me use a horizontal form. H turnstile G over here. Think about this expression itself is just another predicate. Well, it's more like an operator, right? Think about this more like an operator combining two sets of predicates together. So this is a set of predicates for the hypothesis. This is another set of predicates for the goal. And this is more like an operator, which will somehow combine these two sets of predicates, and overall it's also a predicate, right? So this is actually a predicate. And if there's a predicate, that means we can try to either prove it or disprove it, right? Which may be proved or disproved. Of course, right? Either you can prove it or you can disprove it. Let's talk about its meaning on the slides, right? If you can look at the slides over here informally, and once we see the informal meaning, you can tell me how you can formulate it in an unambiguous way using the logical operator that we spoke about before. Let's take a look at the informal meaning. We're saying that this turnstile, the predicate over here, will be true if G can be proved by assuming H, right? Basically, we want to prove G as a goal, but in order to prove it, we can assume H. That's basically what we meant, right? But what if we cannot prove it? In that case, we would say that if we cannot prove G by the assumption of H, in that case, we'll say the entire turnstile is actually false, right? Because G simply just cannot be proved, even by assuming H. And we also say H. You can say H turnstile G. Some people say that. You can also say H entails G or H yields G. So these are the two different ways of saying that, right? You got three different ways to actually say that. You can either say H turnstile G, or you can say H entails G, or you can say H yields G. Either way will be okay. Right? Knowing the informal meaning over here, we know that if you're able to prove G by assuming H, in that case, the entire turnstile, the entire sequence over here will be considered as true, as a theorem, meaning that it's proved as a theorem. So what does it really mean formally, right? So that's why we want to write it down. Let's now try to write it down over here. Okay, let me start with the left-hand side over here. H, let's say, entails G, right? That's the syntax over here. So this is a predicate. So this predicate will be true if and only if. Based on our informal understanding, what does it really mean formally? Well, hopefully you already realize that the informal meaning that we described in the slides is basically corresponding to implication, right? We're basically saying the following. We're saying that in order to prove that G is actually true, it would be sufficient if H is actually true, right? You can see here, I'm just trying to use the different color here to say H is really corresponding to a hypothesis over here, and G is really corresponding to the goal over here, right? So whenever we got a turnstile, it's a predicate. The predicate is proved if only if you are able to prove the G, assuming that H is actually true. That's exactly what implication is about. Right? This formal meaning here is a very simple definition, but you want to make sure you understand the informal meaning as well, just in case you forget. Right? So we talk about this is sequence that we're going to write a lot whenever we want to formulate the proof obligation. But you want to always remember, this is indeed what we are trying to do logically, which is something that we have been doing, since the beginning of the semester by talking about predicates. Right, let me present to you, before I go back to the slide to see this any missing term, I want to talk about this important question over here, which you will see later in the either this lecture here or later lecture. What does it really mean when H is simply just empty? Okay, so let's now see syntactically how can you write it, right? Syntactically, you might say, I simply got the turnstile over here, but I only got a go, but I have this part here is simply just empty. So that'll be one way to write it like that. Or vertically, I can say I got a turnstile over here. I only got G at the bottom. Over here, for this part here, is simply just empty, right? Either way. What do they really mean? Because remember, when we said that the hypothesis is simply a set of predicates. And being a set, of course, may be empty in some special cases. So what do they really mean? Right? We want to know what they are equivalent to. All right. Let me give you one choice over here. Do you think when the hypothesis is actually missing over here, does that mean they're simply just false? Okay. Let me just ask. Right? It's a question over here. So what I will put is, let me put alternative number 1. Let me just use the horizontal form only. Does it really mean it's simply just false? Let me just maybe use maybe false over here as a red, right? Can it mean it's simply just false? And then, and G over here, this will be alternative number 1. Alternative number 2 is missing hypothesis simply mean that it should be as if we put true over here. And then let me just complete the syntax, and I'll let you pause the video and try to think about which one should be the case. But you cannot just guess. you really want to justify why one should work but the other one should not work. You cannot be both, right? Let me say my question again. In the case where the hypothesis is simply just missing, meaning that it's simply an empty set of predicates, in that case, would the sequence over here be equivalent to either when the sequence hypothesis is actually false, or when the sequence hypothesis is actually true? Which one? 1 or 2? Right? You can pause the video and think about it. Right? Assuming that you thought about it, this one should not be the way to go, quite obviously. Why? Well, let's think about the formal meaning. If we adopt this interpretation over here, so that would be equivalent to false, right? We talk about implication over here. So that will be false implies the G. And based on our study of the review of predicates, false implies anything. So which means it will be just true, trivially. So in that case, there's nothing for you to prove, because if you simply got a false hypothesis, you just cannot assume anything. In that case, anything can be proved, and the result will just be true. So that's not what we want, because we definitely want to prove something useful. If you simply put a hypothesis as false, that means nothing useful can be proved, because everything will just be true. All right. So that's why this cannot be the case. That would not be the interpretation where the hypothesis is actually empty. That cannot be. On the other hand, why would this work? Let me use maybe purple over here. So why would this work? And this will be actually equivalent to, let's use the formal meaning again, use implication. So that will be true implies G. And I forgot if we actually talk about this theorem back in the review lecture, but I think for implication, there are two theorems, there are two properties you want to remember. One is called the zero of implication. The other one is called identity of implication. Identity of implication, right? And zero will simply just be, if you say false implies P will simply be equivalent to simply just true. False simply implies anything. So that means you got zero undetermination. So always, if you got false already, it's always true. You have no variance on this part over here. On the other hand, if you actually got true over here, implies P, it will be equivalent to whatever P is. So meaning that, so true as the antecedent will have no contribution, in which case it really depends on whether the consequence over here is true or false. All right. So these, in case I didn't mention about these two important properties in the review lecture, you want to make sure you also understand these two, right? I just put them here, just in case. All right, let's now go back to our discussion about here. So for the second alternative, that would be simply just G, right? Having hypothesis being missing, it would be as if we simply assume true, which is really not very useful in some way, right? Because true is always true. Assuming true, that we are able to prove G, meaning that G itself, without any hypothesis, would just be true anyway. All right. So that'll be the answer. So whenever you actually got, let's say, the turnstile without the hypothesis being empty, in that case, it would be equivalent to this particular turnstile. That's also something very important for you to understand. Very basic, but it's a very good exercise about manipulating the formal meaning for a turnstile, for the sequence. All right, I believe I cover everything over here. Indeed. All right, so we are done with the syntax and semantics introduction about the sequence to you, and make sure you understand everything here. And then the next part, we can talk about if you really want to prove about invariant preservation, how do you formulate in the first place about exactly what is to be proved? That's something we'll see, how to use the sequence to make this expression unambiguous.